Alright, we're going to go over 2.7 and then we'll get a start on 2.8. 2.7 is derivatives and rates of change. And so we just went over 2.1 and there we approximated the slope of the tangent line at x equals a by finding the slopes of secant lines closer and closer to the point a f of a. So that was an approximation, and now we're going to find exactly what that slope of the tangent line is. And what that's called is called the derivative. And so that's its official name, and we're going to call it by that now. But it means the same as the exact slope of the tangent line at a particular x equals a value on a curve. So your book really goes nuts with lots of definitions here. And so the first definitions that we're going to talk about are definition 1 and definition 5, which are really the same thing. And so I'm going to group them together. So one definition with definition 1 and 5 for the derivative at x equals a is that tangent line to the curve y equal f of x at point P at a f of a is a line through P with slope m equals the limit as x goes to a of f of x minus f of a over x minus a. So just a few things here. Notice that we do have the slope equation f of x minus f of a over x minus a, maybe in disguise a little bit here, but really we're just taking two y coordinates and subtracting them on top over two x coordinates being subtracted on the bottom. So you can think of this as like a slope of a secant line that we found in 2.1. But the difference is we're taking this to the next level and we're generalizing this with f of x and x to mean any point. A f of a is at this point P for which we're trying to find the slope of the tangent line at, and we're taking the limit as x goes to a. So we're picking points that are closer and closer to a f of a, and then we're going to take the limit from both sides. So we'll get to the picture for example 1 in a minute, but I just want to scroll down to give a visual of this from the get-go. So what we have here, my a f of a is down here, just make a little arrow here, and that is our point here at which we want the slope of the tangent line, which is shown in purple here, or just like a quick arrow there showing where it says tangent line at x equals a. So we talked about what that means and how to draw it, and that's a pretty good representation there. So what we're doing is we're taking a secant line, which is through a f of a and some other point x f of x. So I'll point to the x f of x here. And this is a specific point on this graph, but let's pretend that it could be any point on the graph. And then note that the change in y is f of x minus f of a, and the change in x is x minus a. So to find the slope, rise over run, we would use the ratio of those two, and if we took that as the limit as x goes to a, we would be picking points that are closer and closer and closer and closer to a f of a, and because it's a two-sided limit, it would be points from both sides. And so that turns out is how we can find the exact slope of the tangent line. And in 2.1 we were experimenting a little bit with those secant lines and approximating that way with specific values. And now we're getting to the point where we're actually throwing that limit notation out front and generalizing this a bit. So let me scroll back up. I sort of stopped halfway through definition 1. One thing I want to show is something called Leibniz notation. So Leibniz notation is something that you're not going to be really responsible for now, but you're going to see it later. So just to put it out there right now, this dy over dx, I'll highlight it. Notice how that looks kind of like, some of you have seen this notation, delta y over delta x. It's the same type of thing. So delta y over delta x, some people may have seen that, maybe not. That's some notation that means a change in y over change in x. So it's like that, but we use a d instead of a delta, and specifically dy over dx means the derivative of y with respect to x. So some special notation there developed by Leibniz, and we'll talk more about him later, or at least I will let this video talk about him, about that a little bit. Not today, another day. And then this line up and down, it's kind of a long line, it's not a 1, and then to say we're doing this at a particular x equals a value is indicated there. So not something you're really responsible for now, but I just want to throw that out there. sometimes Leibniz notation can be very helpful for particular applications of derivatives. Okay, and so to finally finish this definition, it says provided that this limit exists. So that's always kind of a disclaimer for some of these, a lot of these definitions and theorems and such, that the limit has to exist. In other words, it can't be infinity, can't be negative infinity, or it can't be just does not exist in general because the left and the right hand limit don't equal each other, or something like that. There's a lot of reasons why a limit might not exist, and those are just a few. So anyway, getting now to Newton notation. Newton notation is prime notation, so I'll highlight that. We use this a lot. This little prime symbol means a derivative, and so that's another notation we'll use. Notice it doesn't contain as much information as Leibniz notation, and so that's kind of all I'll say for now, but sometimes it's handy to be able to represent more notation. So this is exactly the same definition here. So I just grouped them together. It's just showing that Leibniz notation. So now getting to the actual example, find the slope of the tangent line to the curve y equals x minus x squared at x equals -1. So now we need to do this exactly. We're not approximating anymore. And so I'm going to use this definition I have so far. There's going to be one later that we're actually going to rework this problem with. But for now, this is all we have. So I wrote down what I need to do, and then we're going to start plugging stuff in. So I explained a bit what we're doing. This x f of x is specifically at x equals -5 with a y coordinate of 0.25, but we're not actually going to use that point now. We're going to leave it vary as x f of x, and then we're going to plug in our particular a for this problem at x equals -1. That's our a. We're doing this specifically at x equals -1. And so that will plug in, but the x stuff will be left in general. We're taking that limit at x equals -1. So actually, let's start writing that stuff in. So x is going to -1, and we're going to leave our f of x in general, but I'm going to write in our function, that's important, x minus x squared minus f of a, and so I'm going to plug that into that -1 into our function, so it's going to be -1 minus parentheses -1 squared. And that's all over x minus -1. Alright, so the first step now is to, after plugging in your a, is to go ahead, and your f of x, is to go ahead and simplify a bit, or find f of -1. That's what that's going to boil down to here. So what I have here is x minus x squared, and then finding this quantity here, I get plus 2, and this is all over x plus 1. So now that we have a simpler view here of the function, let's just try to plug in -1. So if we try to plug in -1 to take this limit, what happens? I'm not going to show all the work here, but you can convince yourself you get 0 over 0, which is indeterminate form. Actually, this happens every single time for the definition of a derivative, so you don't even have to bother doing this step once you know that this happens. And if you recall from 2.1, this happened when you try to plug in the point with itself, and that's exactly what is happening here. So it's like trying to find the slope of a point, excuse me, slope of a line would be better. Slope of a line using one point, namely in this case a f of a and itself. And so that's why you get 0 over 0 every time. So now that we know this, we, again, don't have to bother plugging in. This could happen every time. Well, now we had gone over limits because they're important, but largely getting ready for this moment, that now we would be able to tell how to take this limit when we get 0 over 0, this indeterminate form. So you may see that we have a polynomial of a polynomial. The problem child in the denominator is -1 with x plus 1 as a factor. So that means there's a factor of x plus 1 up top. And so factor the top, I'm going to take a negative out of the whole thing, so then it's easier for me to think about how to factor what remains. We have x squared minus x minus 2, and I should be able to factor that with a factor x plus 1. And now that I factored out that negative, it's easier for me to see that this factors into x minus 2 times x plus 1. So then the x plus 1's cancel, and then we should be able to plug in. So let's see what happens. I'm just going to write this out for the sake of showing what happens here. You would probably just plug in here. Now I plug in, so I drop the limit notation. I have x is equal to -1, and what I get is 3. So this means that the exact slope of the tangent line at x equals -1 is 3. It's not approximation, it's absolutely 3. When we determine it with this limit, it's exact. Okay, so I'm going to stop this recording just in case I can't get through the next one. But we're going to redo this example with another definition.